So we're going to look at a classic problem from quantum mechanics, and this is the particle in a box problem. This is the particle in an infinite well, and it's the simplest of all the quantum mechanical problems because the potential energy is zero in a finite region. We're going to do this two ways. We're going to do it by, obviously, we have to take some aspects from quantum mechanics. So we're going to use de Broglie's wavelength, but we're also going to use the standing wave on a string analogy. Now, we know that whenever we trap a wave or bind a wave between two regions, we get standing waves. And that's exactly what we're going to do here. We're going to obtain the wavelength based on what we know for standing waves on a string, standing waves in a air column, any place where we're going to get these two bounded regions, or these two bounded ends, I should call them bounded ends, where the wave is going to reflect off of. So let's get started. Let's go to as classical of an analogy as we can get here. We're going to go with just a little ball bouncing back and forth. And we're going to say that the walls represent a region of infinite energy, that the ball would need an infinite amount of energy to penetrate them, so it just bounces off them. We're going to call them indestructible. But basically, in classical physics, this ball can have any potential energy. Now, to be fair, I haven't shown this ball bouncing back and forth at the energy that it would have given its kinetic energy. But we could imagine if it moved back and forth faster and faster, it would sit higher and higher in this well, because this is a graph of energy vertically and a graph of position horizontally. So again, ball can have any energy from 0 to almost infinity. And again, it's not going to penetrate the walls. So what if we replace our particle, which has definite position, definite momentum, instead with a wave? Well, we're going to replace it with a matter wave. Now, again, for macroscopic ball, the wavelength would be so ridiculously small, it wouldn't really make sense here. So this is more akin to what we get in the situation where we have an electron trapped about the size of, let's say, an atom on the atomic scale, or the last thing we're going to do is look at a proton trapped in an infinite well on about the size of a nucleus. So again, we have these standing waves. We can see that we have our fundamental, our second harmonic, our third harmonic, our fourth harmonic, and this continues all the way to infinity. So we can essentially say, all right, we have one side of the wall, one wall is x equals 0, the other wall is x equals L, and essentially the wavelength is going to be twice the distance between 0 and L, so it's going to be 2 times L, okay, divided by some value of n. So for instance, this is 1/2 of a wavelength, this is 1 full wavelength, this is 3 halves, 4 halves, which is 2, and then of course the next one would be 5 halves, and so on. So we know what the wavelength is for these matter waves. They can't penetrate into the walls, so you have to have nodes at the position of the walls, and that gives the standing waves that we see here. So again, our wavelength is related to the size of the well itself. Here's our fundamental, here's our second harmonic, our third harmonic, and so on. L is equal to the wavelength divided by 2, or lambda, the wavelength, is equal to 2L over n, which is some integer value from 1 to infinity. Okay, so we have the wavelength. What else can we do here? Well, let's use what de Broglie said. We have the wavelength according to just what we know about standing waves. That's from classical physics, so there's no quantum mechanics there. But we will introduce a little bit of quantum mechanics here, and we say that the momentum is equal to Planck's constant divided by the wavelength. I'll plug in the wavelength, and I get that the momentum is 2 times my integer n times Planck's constant divided by L. Okay, a little bit better right there. Where can we go from here? Now, remember, the energy of this particle is going to be all kinetic energy. So in terms of the total energy, when we talk about energy, that, it's the same thing as kinetic energy here, because in this well, the bottom of the well is 0. We know the energy of each of these levels is going to be related to the momentum. So En, the energy of level n, is p squared over 2 times the mass of the particle. So I'm going to plug in p right here. Also going to make a little switch. I'm going to go to the reduced Planck's constant, h bar, which is h over 2 pi. And by doing this, okay, again, only values of n equals 1, 2, and so on are allowed. So En is 4n squared h squared over 2ml squared. 4 divided by 2, of course, is going to be 2. But we also have this reduced Planck's constant put in here. So what we get for this particular case is when we go from h squared to h bar squared, that is going to put a 4 in the denominator. So 4 divided by 4, they cancel out. So I have the energies for my waves. Okay, this is really easy, right? This is not a difficult problem at all. Again, a little bit of classical physics, a little bit of de Broglie wavelength. Classical physics actually tells us that kinetic energy is p squared over 2m. And now I'm going to try to come up with a wave function for this. Okay, I'll do you a favor first. I'll stay away from the e to the I theta form where we have both imaginary and real parts. We'll go back to sines and cosines. But again, we will see a little bit of that later. So once again, our wavelength is 2L over n. I'm going to define k as my wave number. That is 2 pi over lambda, or n pi L. So why am I doing this? Because if I look at this function right here, it's 0 here and it's 0 here. So this is a classic boundary problem thing. I can't use cosine because at x equals 0, cosine is 1. I'm going to use sine here, because sine's a nice oscillating function. I know it describes standing waves. And k here, k is going to have to meet this condition right here, where sine will be 0 at pi, 2 pi, 3 pi, 4 pi, at any n equals pi. So that's why we have that there. N times pi. So my psi x, my wave function, again, remember, the wave function isn't necessarily anything physical for the wave function. It represents the information of that particular quantum state. If this were a wave on a string, it would represent the displacement of the string. But in any case, psi x of psi as a function of x is equal to a sine kx. With this boundary condition over here, that sign will only return back to 0 if, again, we have pi over L, that's his first one, 2 pi over L, that's his second one, 3 pi over L, and so on. So I've formed for my wave function here. The only thing I don't have is my amplitude. And we do know that if I took the square of pi and integrated it over 0 to L, I would be able to get the coefficient out front. But I'm going to leave that for my next phase right here when I do this with Schrodinger's wave equation. So here's my wave function. I have my energies. This is a good test scenario. I want to see if I can come up with the same result if I use Schrodinger's wave equation for this. Now, the beauty of this first method, it was all algebraic, okay? You had to visualize things, but it was all algebraic. You didn't even need calculus to be able to come to the conclusion that we came here. With the Schrodinger's wave equation, we know that it's not so easy in terms of the math. It's partial differential equations, which is fairly advanced. So bear with me as I go through it. Here we go. Now, the time-independent Schrodinger's wave equation looks like this. Why are we using the time-independent? Because my potential energy doesn't depend on position. It's just zero, okay? Well, it doesn't depend on position. But where the wave is, it doesn't depend on position. So, in fact, I can set this term equal to zero, and I just get this term and this term. Remember, we can separate the variables and go from that partial differential equation, which depends on time, where we have a time-dependent term, just e to the negative I omega t, and we have a position-dependent term. That's what we're trying to find out. We're trying to find, these nice little standing waves, because this is what, this is perhaps what the X solution looks like, okay? But the actual time-dependent solution would actually be vibrating up and down once I included that time. So again, my boundary conditions are 0 at x equals 0, 0 at x equals L, okay? I'm going to apply that to whatever solution I get from this. So again, U goes away. It's equal to 0. 0 times anything is going to be 0. So this term goes away. And I get a really nice ordinary differential equation here. I get a second order linear differential equation. Now, if you haven't taken differential equations, that doesn't mean much to you. If you've taken it, you're like, yes, I know what the solutions there are. The solutions for this situation are typically either real exponentials, usually negative exponentials, where the wave function would be decaying, or oscillations, e to the I omega t, I'm sorry about that, e to the I kx, e to the negative I kx. But, of course, when we look at this and we look at the roots, we can see, here's my original differential equation, put together, basically a characteristic equation that's going to tell us if the roots are real or imaginary, and they are imaginary. So that means that my solution for this wave function can be written in terms of sines and cosines. And again, you can do this, a number of different ways. You can do it with, complex exponentials, but really, it's much easier to deal with sines and cosines. Okay, so given my boundary conditions, I'm going to make the same argument that I said before. Okay, before I said, well, I can't really use cosine here because cosine at x equals 0 is 1. That doesn't work. Okay, so my cosine part of the solution has to just go away. So this is an unknown coefficient, b. I can set b equal to 0. That'll get rid of my cosines, and I don't have to worry about the cosines not going 0 at my boundary points. But again, with the sine kx, of course, when x is equal to 0, I mean my boundary condition. When x is equal to L, okay, this has to equal some integer value times pi. So again, this is the condition that I come up with. K equals n pi over L. N can be any integer. So I've just made the same argument that I made before. Okay. So now my wave function looks like this. I can find this coefficient because I know my particle is going to be in that box somewhere. Okay? Particle has to be in the box. The probability of the particle being in the box is 1. So if I integrate psi squared, remember the wave function, if I take the square of the wave function, and then I integrate it and set that probability equal to 1, or I should say if I integrate it over that space, the probability must equal 1. So I do the integration, okay? I put in my boundary conditions, 0 and L. If we look at this, when you evaluate this, you put the a squared on front. When you have sine squared, kx, and you integrate that with respect to x, you get, you get x over 2 minus sine kx over 2k. 4k, sorry. It's right in front of me, and I can't even see it. In any case, we're taking L and 0. So L over 2 minus 0 over 2 just gives me L over 2. Okay. We get, if I put L in here, we've already made that boundary condition. This first term goes away, so that's 0. If I put 0 in here, we get the same situation. Okay. And basically, a squared times L over 2 is equal to 1. Therefore, a must be equal to the square root of 2 over L. So, and my coefficient. There is my little wave function. And for any n, this is going to work. Here is my fundamental. Here's my second. Here's my third harmonic. Here's my fourth harmonic. What's interesting here is the amplitude is independent of the wave function. It's the frequency of the wave function, the spatial frequency. And I get, different values for all of these. Now, what I wasn't able to do for the first standing wave was come up with a frequency. Okay? Yes, I could have come up with a frequency, but let's continue with Schrodinger's equation and try to come up with a frequency. We're going to use the time-dependent equation. So here is my wave function once again. I can, plug this in and say, again, k is equal to n over, I'm going to shorten this up, so we just have k. Basically, we argue that the energy is equal to the momentum squared divided by 2 times the mass. I didn't do a very good job here of deriving this, but again, that goes back to the earlier situation that we had for K. But in any case, as we look at this, again, we have the energy. Energy is P squared over 2m. P is equal to h bar K. We can plug in our value for K. All right. And again, this is our energy. So did we get the same result that we got earlier? All right. This is with Schrodinger's time-independent equation. I said we go into the time-dependent equation. We'll get there in a second. I took a little detour right there. But yes, it is the same thing that we came up with, the same expression for energy that we came up with when we made some of those simple arguments. Okay. Now, where are we? Back to energy. Now we do the time-dependent solution. And this is what's so nice about Schrodinger's equation. This is the hard part, finding the wave function. That's the hard part if wave function with respect to position, if the potential energy is independent of time, because our time-dependent solution is just e to the minus I omega t. So now my full solution here is, here's my position, okay, solution. Here is my time solution. And I have my wave function. And again, if I were to set this in motion, then I wasn't able to animate this, okay? But if I were to set this in motion, you would see, just like you see with standing waves, you see this oscillating up and down. The two would be sort of doing, one antinode would be going up and one antinode is going down. But here's the important thing that we see here. Given the information that we have, given the energy, remember energy is equal to h bar times omega, thus omega is equal to this form right here. Again, we're going back to the energy. We have an h bar up here, but if we divide the energy by h bar, we get back omega. And, just keeping it nice and short, this is all we need for the wave function itself. So what parameters affect the different energy levels? Let's think about this. Well, first of all, the less massive the particle, the smaller this number is, and the higher the frequency becomes. Okay? So, obviously, as we get to smaller and smaller mass particles, they're going to oscillate at higher and higher frequencies. Okay? What else we see is that as L gets smaller and smaller, this is a really important point. As L gets smaller and smaller, these standing wave energies get pushed up higher and higher. Okay, so they start spreading apart further and further as I make this region smaller and smaller. Remember those movies with the walls closing in? Okay, Star Wars had that. Walls were closing in. In any case, as the walls close in, the energy levels would go up higher and higher. Okay, now think of the converse of that. If we expand the wall, we make L larger and larger, the energy levels start getting closer and closer to one another. If we take L to infinity, we get a continuum of energies, and that's what we expect. Okay, that's what we would expect. Why would we expect that? Because we don't have standing waves anymore. Okay, there should be a continuum of energy, both in the classical picture and actually in the quantum mechanical picture. There's no standing wave. Okay, what does the particle in the box really represent physically in nature? Do we have a nice analogy? I can't think of any. Maybe some of these quantum lasers. There are certain lasers that are made with energy, well, I should say, potentials that sort of reflect this square box. But even those are not infinite wells. Those are finite wells, which is a slightly different problem than what we have here. And I almost went into the finite wells, but I decided against presenting that in this course. But let's see how we do. I want to see how we do. Remember what Bohr came up with his energy levels of the hydrogen atom? And the potential for a hydrogen atom looks like this. It's 1/r, right? 1/r dependence right here. Do we get a similar type of situation if I simplify this to just an infinite square well? Well, right off the bat, we've got some problems right here. Okay? My first problem is I should put a negative sign right here. And the second problem is this should be E squared, but let's do that anyway. Again, here's my problem. I make up these slides and then I don't always proofread them, but that is what our equation should look like. So in any case, first thing is in the finite square well, the infinite square well, the bottom of this well is 0. If you look at this, at the center of this well, okay, U is actually equal to, or it goes to, infinity. Okay, right at the center. 1/r, when r equals 0, you got an infinity there. So right there, although it has sort of these steep walls like our infinite well, it's a bottomless pit. Okay, let's just see how we do. I don't want to, worry too much about the details. I'm not using this to model an atom, but if I were, how bad of a hydrogen model would this thing actually be? So, going forward, all right, here is my energy as I calculated it using the infinite square well. I'm going to put a little prime here to indicate that, yeah, I know it's not the real energy level for hydrogen. But the first thing I notice is, oh yeah, I remember when I came out with this, the energy level went by n squared. Okay, well, let me throw in the mass of an electron, the size of an atom, about 1 angstrom, okay, and see what I come up with in terms of energy levels. So go through all the calculations and, okay, 37 EVs. I know with my hydrogen atom, it's 13.6 EVs. So not too far away from there. But here's where things go bad. Here's why this is not a good model. Energy in my infinite square well is proportional to n squared, okay? So as we go higher and higher, the energy spaces are getting further and further apart. That's not true for hydrogen. In hydrogen, as you go to a higher and higher energy, the levels are getting closer together. Remember, the Lyman was from 2 to 1, 3 to 1, 4 to 1, 5 to 1, produced a huge transition that was in the ultraviolet. But when you went from 3 to 2, 4 to 2, 5 to 2, when you're in the Balmer series, the hydrogen spectrum, okay, the jump was smaller, so you were in the visible. With the Paschen series, okay, down to the third level, 4 to 3, 5 to 3, and so on. And it was in the infrared because the jump was even smaller. So my bad hydrogen model, I won't win any awards for modeling a hydrogen atom off of this because it doesn't work, okay? Let's try another one. We failed at this. Let's see if we can fail at another one. The nuclear model. Let's do a proton in an infinite square well. Again, here's my form. We say that the proton is bound within the nucleus itself. And, it's not far from what is known as the EQUA model. But again, a few things. One, we come up with an energy that's not that bad. 2 mega electron volts is not bad from, I think cobalt has close to like a 1.5 mega electron volt gamma ray. But actually, many of the other gamma rays correspond to much smaller jumps. Here again, as you go higher and higher, the energy jump goes by the square of the energy level. The other reason why this is kind of problematic is because in the nucleus, we generally, we don't know everything with the nucleus, but we generally see very similar types of orbits as what we see with the electron going around the atom. The big difference is the potential is very different. The strong nuclear force, sort of goes out to 10 to the minus 15 and then almost disappears and almost drops off. So that's very different from the 1 over r. Well, but we do see some of the orbital angular momentum mechanics that goes into play with the nuclear energy levels. And we'll talk about how this affects the energy levels. So I guess in terms of energy and scale, the energies and scales match the real world pretty well. But a model like this, where the energies just are proportional to the quantum number squared, are not a good model for the atom and not a good model for the nucleus, in my opinion. But we will, however, see a better situation in terms of a real quantum system, which is known as the harmonic oscillator. That's going to be a little bit closer to what we saw with this infinite square well. Why do we study the infinite square well? It's a really easy problem to solve in terms of Schrodinger's equation. It's an easy one to test because all I did, you saw when I started out, all I did is I took the de Broglie wavelength and combined it with what we know from classical physics, and I got my wave functions. Okay, Then I solved the differential equation behind Schrodinger's equations, and got the same result. And that always makes us happy when we get the same result as we predict. Okay,